Welcome to This Explainer. Today we're going on an absolutely wild journey from raw, glowing steel all the way to a perfectly calibrated, high-performance engine. I am super pumped to dive into this with you today because honestly, the behind-the-scenes engineering that goes into the engines powering our world, it's just mind-blowing.
You know, it's crazy to think about, but the daily driver you hop into every morning is actually a massive rolling puzzle made up of over 30,000 individual parts. And for that vehicle to actually get you from point A to point B safely, every single one of those pieces has to fit together flawlessly. We are talking about an invisible, microscopic world where a fraction of a millimeter can literally mean the difference between a buttery smooth ride and a catastrophic failure.
So here's our roadmap for today. First, we'll look at the sheer demand for precision. Then, forging the crankshaft, followed by metallurgy and hardening. After that, we'll dive into the art of machining. And finally, engine blueprinting. Let's jump right in. All right, section 1, the demand for precision. The big takeaway here is that in the high-performance automotive industry, there's virtually zero margin for error. Think about it. If a connecting rod inside your engine is just a few tiny grams too heavy, or if a piston bore inside a brake caliper is slightly, and I mean slightly too large, you're looking at a completely blown engine or total brake failure. The extreme precision we're exploring today isn't just about going fast on a track, it's absolutely crucial for keeping you and your passengers safe on the road. Moving right along to section 2, forging the crankshaft. Now the forging process is, well, it's intense. It all starts by taking a massive steel ingot and blasting it in an oven to roughly 2,400 degrees Fahrenheit. At that crazy temperature, the steel doesn't quite melt into a liquid, but it gets this almost jello-like consistency. Then it's hammered into shape and quickly quenched. The whole goal of this massive thermal shock is to tightly compact the molecules together, which permanently aligns and strengthens the metal's internal grain structure.
And doing that requires sheer brute force. Technicians are out there handling this near-molten steel inside massive industrial hammer presses. And this hammer doesn't just tap it once. It violently strikes the die multiple times to get full closure, coming down with an astonishing impact pressure of 240,000 pounds per square inch. Every single strike. It's just controlled chaos.
During this violent compacting process, a glowing parting line of excess steel actually gets squished out at the mating lines of the die. It's pretty wild. The raw ingot they start with weighs about twice as much as the final product. So all that extra metal being forced out is completely normal, and they just shear it off in a trimming die later on. If you ever spot a faint trace of this trim line on a finished forged crank, it's just a little cosmetic scar from this incredible process.
Okay, section 3, metallurgy and hardening.
There's this fantastic analogy from industry legend Tom Lee. He says, hardening metal is like baking a cake, which is just so spot on. It beautifully explains how different chemical ingredients, things like vanadium, manganese, and nickel, react when they're heat treated. When that glowing hot metal is plunged into a vat of heated glycol to control the cooling shock, all those elements basically grab hands and lock together, building a uniquely strong, unyielding grain structure deep inside the steel.
For high-performance crankshafts, the absolute gold standard is 4340 carbon steel. This specific alloy is basically magic because it perfectly blends carbon with nickel, chromium, and molybdenum, all of which precisely control how fast the metal cools down. Because of that specific chemical recipe, it retains immense toughness even after being heated to over 1,500 degrees Fahrenheit. We're talking about a massive yield strength of 162,000 psi.
But we're not quite done yet. After the initial shaping, these cranks go through a surface hardening process called nitriding. They get sealed in a special container and blasted with heated ammonia and nitrogen gases. The gas chemically reacts with the carbon on the surface of the steel, essentially baking a super hard outer shell right into the metal. It's usually only about 2 to 20 thousandths of an inch deep, but that microscopic layer vastly increases the part's wear resistance and fatigue strength.
All right, on to section 4, the art of machining.
This is where we take a hard pivot from fiery brute force straight into cold, calculated precision. Think about the stark contrast here. We just went from heavy industrial presses slamming metal with 240,000 pounds of force over to an environment of microscopic exactness. To make these raw forgings actually usable inside a motor, they have to be refined down to incredibly tight tolerances using computer-guided CNC machines. This all-digital workflow is designed to guarantee that every single part produced is a flawless clone of the last. It kicks off with an engineer drafting a 3D CAD blueprint. That digital model then tells the CAM software exactly how to program the tool paths. The raw block of high-strength steel is locked securely into the CNC machine, which just goes to work, automatically cutting, drilling, and milling, all while being constantly blasted with specialized cooling fluids to stop it from overheating. Finally, the finished parts are obsessively checked using lasers and coordinate measuring machines. Watching a CNC machine run is literally like watching a master sculptor at work. It effortlessly carves away high-strength steel or lightweight aluminum with just relentless accuracy. For example, the inner walls of an engine's cylinders have to be perfectly round, with a highly specific microscopic finish, just so the piston rings can seal correctly. It's a level of exactness that human hands just couldn't replicate in a million years.
Which brings us to our final section, Section 5, Engine Blueprinting. This is the final puzzle piece, where cutting-edge mechanical engineering finally meets human expertise. Blueprinting an engine isn't just slapping a bunch of parts together. Far from it. It's a highly specialized, meticulous process where master technicians tear an engine down, precisely measure every single component, and carefully reassemble it to the manufacturer's exact mathematical specifications. It's all about extracting maximum efficiency, power, and lifespan. You really can't automate this part. Mastering this trade takes serious, hands-on training. In advanced automotive programs like the Power and Performance courses over at UTI, students really get into the weeds. They're learning how to run a flow bench to optimize cylinder heads. They're calculating complex compression ratios and diving deep into camshaft theory. Lift, duration, timing, the whole shebang. They use insanely precise tools like dial bore gauges and micrometers to ensure everything operates in perfect harmony. They're the ones bringing all those cold machine parts to life. So, as we wrap up this explainer, I want to leave you with something to chew on. Next time you marvel at your car cruising smoothly down the highway, or really any complex machine doing its thing, think about what it took to get there. The 2,400 degrees of heat, the 240,000 pounds of crushing pressure, the sub-millimeter computer machining, and the expert human touch. What other everyday objects do we all rely on that are hiding this incredible, invisible level of manufacturing precision? Thanks so much for hanging out and exploring the life cycle of a high-performance engine with me today.